The quantum chemistry and spectroscopy. This subject, as it was introduced at the lecture contains, there are 5 subtopics, namely, the first one is the orbital angular momentum. The second one is the SCFMO of the polyatomic molecules. The third one is the basis functions or bases. The fourth is the population analysis and atomic charges. The last one is the semi-empirical method, which is the simplest method of the quantum mechanics. The topic of orbital angular momentum. As we know that electrons in atom have 2 types of angular momentum. The first type is the orbital angular momentum, and the second type is the spin angular momentum. Nevertheless, the spin angular momentum must come with the orbital angular momentum. The important topics of the orbital angular momentum can be separated into 3 topics. 1.1 is the angular momentum operators. The detail of the operator and their commutation relation will be presented. 1.2 Schrödinger equations in spherical coordinates. The Schrödinger equation will be mentioned to describe the angular momentum in terms of orbital angular momentum and spin angular momentum. 1.3 The angular momentum in applications. The angular momentum has many more fundamental applications and can describe the structure of atoms, describe the rotation of the molecules, and all forms of spectroscopy. The angular momentum operators. Angular momentum plays a central role in both classical and quantum mechanics. In quantum mechanics, angular momentum plays a principal role in understanding the structure of atoms. There are several operators of angular momentums. As I mentioned that there are 2 types of the angular momentum. The first one is the orbital angular momentum. The second one is the spin angular momentum. We use the L and S symbol respectively. Therefore, the total angular momentum J can be computed using the equation 1.1. J is the total angular momentum vector. L is the orbital angular momentum vector, and S is the spin angular momentum vector. If the position of the particle traveling is expressed in terms of the components of the vector, R can be written as xi plus yj plus ck, where I, j, and k are orthogonal unit vectors. Therefore, The linear momentum can be expressed in terms of its component as well. Therefore, P is equal Px I plus Pyj and plus Pck. We can substitute R and P into the equation 1.2 of the angular momentums. The classical expression for angular momentum L can be modified from equation 1.2 L equal to R cos P. To get the equation 1.4 in terms of determinant, the determinant right hand can be expanded using mathematical formula. Now we get the equation 1.5. Angular momentum is equal to the first term is y pc minus z py multiplied with the unit vector I plus the second term cpx minus xpc multiplied with the j vector plus the last term xpy minus ypx multiplied with the k unit vectors, where I, j, and k are orthogonal unit vectors along the x, y, z axis respectively. To form similar equation of position r and momentum p in terms of their components, therefore it follows that the angular momentum can be expressed in terms of its component as shown in equation 1.6. Angular momentum is equal to the component Lx multiplied with I vectors plus Ly multiplied with the j vector and plus Lc multiplied with the k vectors. If we compare the equation 1.6 with the equation 1.5, therefore we can get the identification of three components as shown in equation 1.7, namely Lx is equal to term ypc minus zpy, and the next component Ly equal to term zpx minus xpz, and the last component Lz is equal to term xpx minus ypx. Each component can be generated from its predecessor by cyclic permutation of the x, y, and z components. The magnitude of the angular momentum, denoted as L squared, is related to its components by the normal expression for constructing the magnitude of L vectors. Modification from equation 1.5 become equation 1.8, namely L squared is equal to the summation of its component of the angular momentum square. Therefore, to be consistent with the equation 1.8, that none of the components exceeds the magnitude. That means that the value of the absolute LQ of each component should be equal or less than the L value. The definitions of the components and the magnitude to carry over into quantum mechanics with the position Q and the momentum PQ in the definitions of the angular momentum components LQ. Interpreted as operator, the operator LQ in the position representation can be obtained by replacing Q by Q time and momentum PQ by H bar over I time the operator partial differentiation with respect to position Q. In the equation 1.7, then we can get the new equation 1.9. H bar is a symbol as a reduced Planck constant. Its value is equal to Planck constant over the value 2 pi, or equal to 1.054573 times 10 power minus 24 joules second. To make progress, we need to establish the commutation relations of the orbital angular momentum components LQ operators. Let's consider the commutator of the component Lx and Ly. Due to the equation 1.7 and the commutator formula, A commute with B equal to AB minus BA. Therefore, the commutator between Lx and Ly can be the first equation. We can expand, we can operate, and then we get the fourth equation. The fourth equation, if we replace the Lz function, we will get the equation 1.10. The detail I will give you to solve, to prove as the homework. The similar delight process for the equation 1.10. The equations 1.11 and 11b are therefore obtained. Equations 1.10, 1.11, and 1.11b are assigned as the homework. The homework assignment sheet will be uploaded on the board. The remaining operator is the L-square operator, which is corresponding to the square of the magnitude of the angular momentum. We need its commutator with the operator LQ or angular momentum components, and proceeds as follows. The first, we write the commutator between L square and LZ as shown in equation 1.12. We have used the fact that the commutator of the LZ square and LZ is 0. Therefore, LZ square and L0 is commutator equal to 0 as shown in equation 1.13. Next, consider the following commutator, which we developed by drawing on the three fundamental relations derived above. Therefore, Lx squared commute with Lz equal to minus I h bar and term Lx Ly plus Ly Lx in the equation 1.14. The next equation, similarly, the commutation between Ly squared and Lc is equal to I h bar multiplied with the term Lx Ly plus Ly Lx in equation 1.15. The sum of Lx squared commute with Lc and Ly squared commute with Lc is also 0. So, we can conclude that the commutator of L squared with Lc is 0. Moreover, because Lx, Ly, and Lc occur symmetrically in L squared, all three operators must commute with L squared. If any one of them does, that is, Lc squared commute with Lq or commute with angular momentum components equal to 0 as shown in equation 1.16. For all position Q, the equation 1.16, the commutation between Lc squared and Lq is equal to 0. The commutation relations in equation 1.11 and 1.16 are the foundations for the entire theory of the angular momentum. Whenever we encounter four operators having these commutation relations, we know that the property of the observable they represent are identical to the property we are about to derive. Therefore, we shall say that an observable is an angular momentum if its operator satisfies this commutation relation. This slide is the topic of Schrödinger equations in spherical coordinates. We will relate the Schrödinger equation to the angular momentum. The Schrödinger equation in spherical coordinates was derived from the fundamental Schrödinger equation in equation 1.17. This equation expressed as I h bar times the differentiate the wave function with respect to time is equal to the Hamiltonian operator time wave function. The Hamiltonian operator H is obtained from the classical energy. Therefore, we can write the equation of the classical energy. Half m v square plus v potential v is equal to 1 over 2m of p square plus potential energy v, and we obtain the summation of the momentum square of each component px, py, and pc as shown you. From the formula of the momentum components, px, py, and pc is equal to h bar over I times the operator differentiation with respect to component x, y, and z respectively, or we can write as the p equal to h bar over I and time symbol del. This symbol we may call the nabba or del. By replacing equation 1.19 into the equation 1.17, the new Schrödinger equation is therefore obtained as the equation 1.21. The left hand I h bar multiply differentiation of wave function with respect to t is equal to the h bar square over 2m. M is mass of particle. Multiply Laplacian operator on the wave function side plus potential energy V multiply wave function psi. The Laplacian operator in Cartesian coordinate can be written as equation 1.22. Laplacian operator is summation of the operator of the secondary derivative with respect to each component x square, y square, and z square. The potential energy V and the wave function are now the function of the displacement R. This is a function of the x, y, and z coordinate, and the function of time. Therefore, the possibility of finding the particle or electron in the infinitesimal volume is equal to the absolute square of the wave function multiplied with the volume d r power 3. Thus, the normalization condition for the wave function over all space can be written as integration over absolute square of the wave function d power 3 are equal to unity or 1. The time independent or the independent of time of the wave function can be derived from the time dependence equation 1.24. The wave function is the function of r and t time of the stationary state n is equal to the wave function n depending on the radius r, time e power minus I e n r over h bar. Where the spatial wave function satisfies the time independent Schrödinger equation. Therefore, we just use the first term of the wave function as a function. Therefore, the equation 1.24 can be written as the new form using the time independent wave function n. The general solution of the time dependent Schrödinger can be written also as the equation 1.26. Wave function n state equal summation of the parameter c of the wave function n depending on r multiply e power minus I e n t over h bar. For the parameter Cn or the constant Cn can be obtained from the iteration of the initial wave function. Initial wave function, we can use this symbol function in the r, 0. The Laplacian operator in Cartesian coordinate, as shown in the equation 1.22, can be expressed in the spherical coordinate as equation 1.27. By replacing the equation 1.27 to the 1.25, the equation 1.28 is therefore obtained. To replace equation 1.29 to equation 1.28, the equation 1.30 is obtained. The radius r and the angle theta and phi of the particle depicted in the figure 1.2. The radius r mean this vector, and for the angle theta we call polar angle, and for the angle phi we call azimuthal angle. To rearrange equation 1.30 by dividing with the ry and multiply by minus 2mr square over h bar square, we can obtain the equation 1.31. After we arrange the equation to get the equation 1.31, it can be seen that the first term of the curly bracket depends only on radius r, whereas the remainder part, this part, is the part depend only the angle theta and phi. Accordingly, each must be constant. For reasons that will appear in due course, this can be written separation constant in terms of L multiply L plus 1 as term of the angular momentum. Again, from the equation 1.31, the left hand side is a radial part plus the angular part surrounded with the red dot line. In terms of the L times L plus 1 term of the angular momentum, therefore we can say that the first part surrounded with the blue dot line is equal to L multiply L plus 1. And for the last part, the angular part should be the minus L multiplied with L plus 1, because to get the result of the zero of the equation 1.31. The topic of the angular momentum in application. There are several applications of the angular momentum. In this slide, just shows properties of the angular momentum on its applications, such as the first, angular momentum is well related to rotational motion of a system of particles, in this case is the electrons. It is essential for understanding the infrared and microwave spectra of a molecule and the properties of the electrons in atoms. The second, the electron spin or nuclear spin is an angular momentum that has no classical analog. The third, the spin is accompanied by magnetic moment, which means that we can change the energy of the particle by acting on it with external magnetic field. The NMR and ESR spectroscopy are based on this ability or behavior. The fourth, a good understanding on angular momentum brings together understanding on spectroscopic technique. The applications of angular momentum based on the hydrogen atom as representation of studies particle let us to get the modification of time independent Schrödinger equation 1.28 for hydrogen atom. The Schrödinger equation is therefore reduced as shown in equation 1.24 for the hydrogen atom. Mu is reduced mass of electron, R is radius. Angular momentum in Z component LC is the angular momentum operator of C component. The Schrödinger equation for the hydrogen atom, equation 1.34. The first term is the radiokinetic energy and the potential energy VR. You have also learned that the Hamiltonian H of the hydrogen commutes with L square and LC. This means that the Hamiltonian H, L square and LC have common eigenstate denoted by NJM function. The state NJM function, the energy of atom can be as shown in the equation 1.35. As we learn, the orbital angular momentum is quantum number and related quantum number are as follows. The first is the principal quantum number denoted by small n. The second is the Israel orbital angular momentum quantum number, denoted by small l letter. The third one is the magnetic quantum number, denoted by small m letter or m subscript l. The next is the spin quantum number, denoted by small s or m subscript s. The possible value and property of these quantum numbers are shown in following table. The first column is the quantum number symbol. The second column is the name. For the name of the angular momentum, we may call secondary or azimuthal or angular momentum. For the labels of the principal quantum number, it labels for electron energy level or shell number. Therefore, its possible value is the integer 1, 2, 3, 4, 5. For the property of the orbital size and energy level. For the angular momentum quantum number, label for orbital type as the S, P, D, F orbital. For possible value is the integer from 0 to n minus 1. Its property is the orbital shape or sub-level or subshell. For the magnetic quantum number, label for the orbital subtype and its possible value is the integer from minus L to plus L. The property is the orbital orientation. The last one, spin quantum number, label the electron spin. Their value is the plus half and minus half. The property is the electron spin direction up and down. As the square of the angular momentum, its value is the h bar square times j plus 1 when j is the total angular momentum. And the projection of the angular momentum on the z-axis is the h bar m. The Hamiltonian operator operates on the state in Jm can be the value as shown in the equation 1.36. And for the L square operator operate on the state in Jm can be found as the equation 1.37. The last one is the LZ operator operate on the function or state of the NJM, and the eigenvalue is equal to h bar times m, as shown in the equation 1.38. We can note that J indicates the eigenvalue of the L square and M indicates the eigenvalue of LC. We learn from this example that the eigenstate of the L square and LC may also be eigenstate of other observable that commute with the L square and LC. In this case, the energy. These eigenstates are labeled by additional quantum number n. In this case, they are the function njm. A similar situation appears in the case of the diatomic molecules. If we make the rigid loader approximation and the harmonic approximation, the eigenvalue equation for the energy in equation 1.34 becomes the equation 1.39. In case of the diatomic molecule, the vibrational energy can be solved using the eigenstate R psi function equal to nu Jm function. The vibration energy is therefore equal to h bar times omega multiplied with the nu plus half, where omega is the vibration frequency and nu is the vibration quantum number. We can conclude that when L square and LC commute with other operator, their eigenstates must be eigenstates of those operators. When we need to make this explicit, these eigenstates will be labeled as the state A, J, M, where A tells us the value that the quantities represented by these other operator takes. When the system is in the pure state A, J, M, and a measurement is made,